Hello, and welcome to the lecture on 3.2. Today we're going to talk about polynomial functions and their graphs. Start off with the polynomial functions. A polynomial function of degree n is a function of the form p of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down to a sub 1 x plus a sub 0, where n is a non-negative integer and a sub n is non-zero. Now we've discussed this before, what a polynomial is. I think I've written out this definition a few times already throughout the semester. So we should have a pretty good handle of what these are so far. The numbers a sub 0, a sub 1, all the way up to a sub n are called the coefficients of the polynomial. I've referred to them as coefficients in the past, and this is the reason. The number a sub 0 is called the constant coefficient or the constant term. And that's because a sub 0 is its own term. Remember, a term is its coefficient times x to whatever power. So this would be the x to the n minus 1 term. This would be the degree n term, degree 1 term. But that term includes the coefficient and the variable to the power. A coefficient refers to only the constant number in front of the variable. So when we say a sub 0 is a constant coefficient, it's because it's only a number. It's attached to x to the 0 power, if you want to think about it that way. But it's also its own term, which is why we can call it the constant term. The number a sub n is called the leading coefficient, and the leading term is a sub n x to the n. Now, a sub n x to the n is the highest degreed term, so it's called the leading term. The leading coefficient is just the number in front of the highest degreed variable. Let's go ahead and do an example here. Suppose that we have the function 2x to the 4th minus 3x cubed plus 20x squared minus 15x plus 12. There's a few things here. This is called your constant coefficient. We have our leading term, our leading coefficient, and our degree. And we didn't define degree here, but we have defined it before, so I expect that we remember this. All of the coefficients are 2, -3, 20, -15, and 12. We've gone over some of these graphs before in section 2.2, but I'm going to go over some of these again, specifically the polynomial ones. We're only going to go over the power functions. This one would be y equals x squared, and then we're going to talk about y equals x cubed here, y equals x to the 4th. Y equals x to the 4th, as I've stated before, should be a lot flatter here. Notice that the x squared curve is a lot rounder than the x to the 4th. This is a lot flatter between -1 and 1. Same idea with x to the 3rd and the next one I'm going to graph, which is y equals x to the 5th. Let's say that we have x equals 1/2. 1/2 squared is equal to 1/4. 1/4 is smaller than 1/2, which is why we get this bend. If we take 1/2 and cube it, we get 1/8, which is even smaller than 1/4. So we get an even flatter surface here around x cubed. X to the 4th. This would be 1/16. And 1/16 is much smaller than 1/4, but they're going to have the same general shape. So at 1/2, this y value should be 1/16 here, but only 1/4 here. Similarly here, for x to the 5th, we take 1/2 to the 5th, then we get 1/32. So what that means is that the y value at 1/2 should be 1/32 versus x cubed, which would be 1/8. A polynomial with a single term is called a monomial, mono meaning one. So the graphs that I showed on the previous slide are all graphs of the monomials y equals x squared, y equals x cubed, y equals x to the fourth, and y equals x to the fifth. Now I want you to try one. You're going to have to use some knowledge from previous sections. Use one of the above graphs to graph y equals x minus 1 to the third power. The next topic I want to talk about is the end behavior of polynomials. So let's start with a note. I want to show you why the end behavior acts the way that it does before we get into it. As x gets large, the dominant term is the highest degree term. Now let's show you why this is. Suppose that we have the function f of x is equal to x squared plus 4x plus 100,000. So near x equals 0, the dominant term is 100,000 because it's the one that's contributing most to the y value. So let's say that x is 0. Then 100,000 is contributing everything to the y value because the other two terms turn out to be 0. If x is equal to 1, then we have 1 squared plus 4. That's only 5. But the y value in totality would be 100,005. The 100,000 is coming from the constant term. So near 0, when x is near 0, the y value is most dominated by this constant term. For right now, for this particular function. It's not always the case. But what is always the case is as we get larger and larger, the dominant term will shift to the highest degree term. So let's look at x here, and let's look at our y value, which is going to be x squared plus 4x plus 100,000. Something like this. Okay. So as I stated before, when we have, if x is equal to 1, then we have 100,005. And again, the dominant term would be the 100,000 here. Now if x is equal to 10, we would get 10 squared plus 40, so this would be 10 squared, which is 100, plus 40 plus 100,000. So the 100,000 is still dominating this term, but it's not dominating it as much. 100,000 out of 100,005 is a much higher ratio than 100,000 out of 100,140. These terms are growing, and they'll grow a lot faster as x gets larger. Now remember, we're trying to let x get as large as possible, meaning that x is going towards infinity. So when we think of 10 in comparison to infinity, it's insignificant. It's minuscule. It's like an ant compared to the universe. It's nothing. So let's make x even larger. Let's say it's 100. Well, now we're getting closer and closer to this 100,000 mark because 100 squared is 10,000 plus 400 plus 100,000. Now still, 100,000 is the dominant term because again, it contributes the most to the y value. It's contributing 100,000 versus 10,000 or 400. 10,000 is still pretty small relative to the size of 100,000. It's 1/10 of the size. But once we reach the x equals 1,000, now the x squared term is going to start dominating because now we have 1 million. Because 1,000 squared is 1 million, plus 4,000, plus 100,000. Now hopefully you see, as x is increasing, this x squared term is increasing faster than x is because of the square. Now the x term is of course increasing at the same rate. If x is 10, we get 40. If x is 100, we have 400. If x is 1,000, we have 4,000. This term is growing at the same rate, or relatively the same rate, as x, but the x squared term is not. It's growing even faster than x. And we can see here now that 1 million is the dominant term. And we're only at x equals 1,000. Still insignificant compared to the value of infinity. Remember, x getting large, you're talking about trillions. You're talking trillions is even small compared to infinity. So let's go one more and do 10,000. Now 10,000 would be 100. 10,000 squared is 100 million. So now it's very clear that x squared is dominating this y value. 100,000 is insignificant compared to 100 million. It's only 1/1000th of 100 million. It's insignificant in comparison. So even though 100,000 is a very large number when we just think about a number, when we talk about it compared to the x squared term, when x is 10,000, this is nothing. 100,000 is nothing compared to 100 million. So as you can see, as x gets larger, the x squared, because we're squaring it, we're multiplying that x by itself, we're getting a huge number. So as x gets larger and larger, the dominant term turns to the highest degree term. And we can see that with the x term as well. X is still insignificant compared to x squared as x gets larger. Now at the very beginning, when x is 1, this term is still dominant over this term, but again, 100,000 is dominant over both. But 4 times 1 is much bigger than 1 times 1. So now let's go into what the end behavior of polynomials look like. And I need to note here also that we are talking specifically about polynomials. We'll talk more about end behaviors of different types of graph later on, but for right now, we're just talking about polynomials. The end behavior of the polynomial p of x equals a sub n x to the n plus all the way down to a sub 1 x plus a sub 0 is determined by the degree n and the sign of the leading coefficient a sub n, as indicated by the following. So, as we noted before, notice that when we have an even n, our end behavior is up, up. Why is that? When we think about x going to negative infinity, when we have an even degree, that negative will be multiplied by itself and it'll cancel out. So we'll end up with a positive y value. So when we let x go to negative infinity, when we have an x squared, that negative will cancel out because it's squared. So our y value will be positive and increasing in value as we move left. As we move to the right, x going to infinity, we would have a positive times a positive. So we also have a positive y value. Now with an odd degreed function, it's a little bit different because as x goes to positive infinity, we would have a positive times a positive times a positive, which is positive. So as x is going to infinity, y being x cubed will also go to positive infinity. But as x goes to negative infinity, we would have a negative times a negative times a negative, which is negative, which is why we get negative y values here. Now, as x gets larger and larger in the negative direction, we'll end up with negative y values that are getting larger and larger in the negative direction as well. So if, let's say that n is even and a sub n is greater than 0, here we'll say that n is odd and a sub n is greater than 0. Here we'll graph when n is even and a sub n is less than 0, and here n will be odd and a sub n will be less than 0. Now the a sub n is important because if a sub n is negative, it would be as if we had a negative in front of one of these graphs. So let's say that we had a negative in front of this x squared. Then no matter how large x gets in either direction, x squared will be positive, but if we have a negative in front, multiplying a positive number times that negative number that's in front of x will give us a negative number. so we would actually go down instead. It's a reflection over the x-axis. So if we have even, n is even, and a sub n is positive, then this positive coefficient will not change the sign of the leading term. And n is even means that as x goes to infinity, our y is going to infinity because we would have a positive times a positive, and as x goes to negative infinity, we would have an even number of negative numbers multiplied together, which would give us a positive. So we would end up with a positive y value going to infinity. So we would have up, up as our end behavior. As x approaches negative infinity, as x goes to negative infinity, y goes to positive infinity. Similarly, as x goes to positive infinity, y goes to positive infinity as well. Now for this one, it's a little bit different because we have an odd n. So we have an odd degree on our leading term. So we're multiplying x by itself an odd number of times. Now that doesn't matter when we go to infinity because a positive times a positive times a positive is always positive. No matter how many times you multiply positive numbers together, you're going to get a positive number. So as x goes to infinity, as long as we have a sub n being greater than 0, so we're not changing the sign of our leading term, we would have a positive, we would have that our y is going to positive infinity. Now, because n is odd, if x is negative, then we would have an odd number of negative numbers being multiplied together. So let's say that x is negative 10. We would have an odd number of negative 10s being multiplied together, which would give us a negative value. So we would end up with a negative infinity for our n behavior, because our y value would be going to infinity, but in the negative direction, because of the odd degree and x being on the negative side. So here, as x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. Now down here on these bottom two graphs, we have a negative a sub n. That means that we're changing the signs of all of our x terms. We're changing the sign of the result upon plugging an x in. So if we have an even number, if we have an even degree, and x is going to infinity, we would have a positive number being multiplied by itself an even number of times. But because we're also multiplying by a sub n, and a sub n is negative, we would get a negative value down here. So as x goes to infinity, we would end up with y going to negative infinity. That's because a sub n is less than 0. Similarly, as x goes to negative infinity, those negative x values would be multiplied by each other an even number of times, so we would end up with a positive value if we just plugged in an x value. But once we multiply by a negative a sub n, then we get a negative value. So as x goes to negative infinity, our y value is also going to negative infinity. So we end up with this, that the end behavior is down, down, when we have a sub n is less than 0 and an even degree. Now similarly here, if x is going to positive infinity, we would have, upon plugging in an x, this part of the first term would be positive, but then we would multiply by a sub n, which would give us a negative value. So as x goes to infinity, x to the n is going to infinity, but a sub n times x to the n is going to negative infinity. And again, that's because a sub n is negative, as we assumed in this particular graph. Now, if x is going to negative infinity, we have an odd n, we have an odd degree, which means that any negative x value will be multiplied by itself an odd number of times, which will give us a negative value. But we take that negative value when we multiply it by a negative a sub n, and we would get a positive value. So as x goes to negative infinity, y goes to positive infinity for this particular case. So if n is even and a sub n is positive, we have up, up as our n behaviors. If n is odd and a sub n is positive, we have down, up for our n behaviors. If n is even and a sub n is negative, then we have down, down for our n behaviors. And if n is odd and a sub n is negative, we have up, down for our n behaviors. And those should follow here as well, because these are just special cases of these polynomials. So when we look at these graphs, we always have a positive a sub n. So any even degreed polynomial would end up having n behavior up, up for any even. And then if we have an odd degreed, it should be down, up, as we see here. Let's do an example here, just to sort of get through these a little bit. Suppose that we have x to the fourth plus 4x plus 1 as our function. Now we want to know what the n behavior is, and that's all we're looking for. So as x goes to infinity, what's happening to the y value? Well, we have an even degree, and we have a positive leading coefficient. So here, n is equal to 4, that's even, and a sub n is equal to 1. That's the leading coefficient here. So we would end up with, as x goes to infinity, y is going to infinity, and as x is going to negative infinity, y is going to positive infinity. And if you plug in some large numbers on both sides of x, you should be able to determine that you would have a up, up as your n behaviors. Let's do part B now. Negative 3x cubed minus 12x. Suppose that we have this graph now. Let's start with negative infinity this time. Now, as x is going to negative infinity, so we're moving to the left, we need to figure out whether our y is going up or going down. Well, we have a negative coefficient. We have a negative leading coefficient, which is going to be negative 3, and our n is odd, because it's also 3. Our degree is 3, our leading coefficient is negative 3. Okay, now as x goes to negative infinity, that means these negative numbers are going to be multiplied by themselves 3 times, which will be a negative value. But we're also multiplying by a negative 3 because of the leading coefficient, which will mean we'll have a positive value here. And then as x goes to positive infinity, what's happening to y? Well, if x is going to positive infinity, plugging in a large positive number here, say 1,000,000, then we would have 1,000,000 cubed. That's a positive number, but then we're multiplying by the negative 3, which gives us a negative number. So we have a n behavior of negative infinity here, just like this. All right, I want you to try one now. Determine the n behavior of the function f of x is equal to x to the 31st power minus 12x squared plus 51. You're just looking for the n behavior here. All right, the next thing we're going to talk about is using zeros to graph polynomials. For this topic, we need to go over a couple of things so that we can graph some polynomials on later topics here. If p is a polynomial function, then c is called a zero of p if p of c equals 0. Another term for this is a root. We would say that c is a root of p as well. Now we've gone over that definition before. Here what I want to talk about is some identical terminology. Real zeros are polynomials. If p is a polynomial and c is a real number, then the following are equivalent. 1, c is a 0 of p. 2, x equals c is a solution to the equation p of x equals 0. 3, x minus c is a factor of p. 4, c is an x-intercept of the graph of p. So what we're saying here is that each of these mean the same thing. 1, 2, 3, and 4 are identical statements. I'm going to prove it for you on this slide here. If you don't want to see the proof, it's okay. You can skip through this part. If we're going to prove 1 to 2, we start with C is a 0 of P. That's 1. And definitionally, what this means is that P of C is equal to 0. A solution has a similar definition. If we say that x is equal to c, this then means that P of x is equal to 0. So if x is equal to c, then P of x is equal to 0, as stated here. Because all we're doing is replacing c with x and saying that x is identical to c. This is 1 to 2. 2 to 3, what we start with is if x equals c, then P of x is equal to 0. This is our assumption. We know this to be true. We need to move to x minus c being a factor of P of x. So here what we're going to do is we're going to say, well, P of x is going to be equal to Q of x times x minus c plus r of x. This follows from the division algorithm. Now, what we need to show here is that r of x is equal to 0. What we know, if x is equal to c, then P of x is equal to 0. So if x is equal to c, then on the left we have 0, which is P of x, which is going to be equal to Q of x times x minus c plus r of x. But if x is equal to c, then we get that this is 0. Because x equaling c means c minus c is 0, and we get 0 times q of x. So then we have r of x is equal to 0 as well, which is what we wanted to show. This then implies that P of x is equal to q of x times x minus c. And this is from 2 to 3. So far we have the first statement implies the second statement implies the third statement. Now we need to show that the third statement implies the fourth statement. We start with the assumption that x minus c is a factor of P of x, which means that P of x is equal to q of x times x minus c. Now what we're trying to get to is that c is an x-intercept of P of x. So y equals P of x will be 0 when x is an x-intercept, which means we would have this statement here. 0 is equal to y, which is equal to P of x. P of x is equal to q of x times x minus c. Then we have the zero product property of q of x and x minus c. So either q of x is equal to 0 or x minus c is equal to 0, which implies that x minus c, or x equals c, is an x-intercept. Because the point c0 is on the curve. This would be 3 implies 4. And then we just need to show that 4 implies 1. So we start with the assumption that c is an intercept of P, which means that c0 is on the curve. So what we have here is that when x is c, then y is 0. So we have 0 is equal to y is equal to P of c, which implies then that c is a 0 of P of x, which is what we wanted to show. So we have that 4 implies 1. So now we have 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. They're just different ways of saying the same thing. The next topic I want to talk about is the intermediate value theorem for polynomials. If P is a polynomial function, where P of A is less than n is less than P of B, then there is a number C such that A is less than C is less than B, where P of C is equal to n. This is the intermediate value theorem. What we're saying here is that if we're given a P of A, so P of A would be the y value associated with the x value A, and we're given a P of B, which would be the y value associated with x equals B, then if n is somewhere in between, let's choose a random n in between P of A and P of B. So n could be anywhere between here. Let's just choose a random number, call it n. Then there exists a C on this interval such that P of C equals n. Now what that means is that we can choose an n value anywhere between P of A and P of B, and it will be associated with a corresponding C value that's between A and B. So suppose that we chose this n, then this would be the C value. But if we chose a different n, we would get a different C value. Get C value here. So what the intermediate value theorem is basically saying is that every y value is achieved between P of A and P of B by some x value that's between A and B. So choose any y value, then there's a corresponding x value that the function maps to that y value that you chose. That's the intermediate value theorem. Let's do an example. This is probably the most common type of example that books use in this section. Show that P of x has a 0 on the interval 0 to 2, where P of x is equal to x squared minus 2. So there's a couple things we need to figure out. First, we're trying to show that there exists an x-intercept. There exists an x value that maps to y value 0. So what we need to make sure is that our P of A is below 0 and our P of B is above 0 so that our n can be equal to y equals 0. So here we check the endpoints. P of 0 will be negative 2. P of 2 is equal to positive 2. So the y value 0 is between negative 2 and positive 2. So we can choose it as our n. Now, I don't really care which x value is associated with y value 0. All that I care about is that one exists. So we say that since P of 0 is equal to negative 2, which is less than 0, and 0 is less than 2, which is equal to P of 2. So here what I'm saying is that your A is 0 and your B is 2, and 0 is between those two things. So we've met the condition here. P of A is less than n is less than P of B. Since that's the case, and we have a polynomial, we know that there exists a C on the interval 0 to 2 such that P of C equals 0, which tells us that there is actually a 0 on that interval, which is all we wanted to find. We don't actually need to find the value of x. We just need to show that there is an x value that maps to 0, and we've done that by using the intermediate value theorem here. So whenever you're using a theorem, you want to make sure of a couple of things. You need to meet the conditions that are laid out in the theorem. For instance, here, the conditions are that P is a polynomial, which we stated. Our P of x is a polynomial, and we stated it in our solution. P of x is a polynomial. And we need to meet the condition where n is between P of A and P of B, which we also met. P of 0 would be the same thing as P of A, where A is equal to 0, and P of B, where B is 2, are negative 2 and 2 respectively, and 0 is between those two values. So since we meet that condition, this condition here, and that P is a polynomial, then we know that the conclusion of the theorem is also true. And the conclusion is that there is a number c between a and b where p of c is equal to n. And of course, in our problem, n was 0. Okay, we're going to do a different type of example here now. We're getting to a point where we can combine a few of the things that we learned so that we can try to graph an equation. First, I want to note, we know zeros occur at factors of p. If our p of x is equal to x cubed plus 4x squared minus 4x minus 16, and we want to graph this, we can find the zeros immediately. Here, what I'm going to do is group the first two and the last two. Do a plus and negative here so that we have a positive sign in between the two parentheses. Factor out what you can. You get x squared here. Factoring in x squared out of x cubed, we're left with x plus 4. Plus factor a negative 4 out, and we have x plus 4. Then you should be able to see that we have x4 that's common in both of these terms. So I'm going to factor that out next, and we're left with x plus 4 is factored out, and we're left with x squared minus 4, which is a difference of squares, so this factors into x plus 4 times x plus 2 times x minus 2. So we factored p of x. We know now that p of x has zeros at these values, at negative 4, at negative 2, and at positive 2. So if we're going to try to graph this, then we need to do a few things. Let's go ahead and draw our axes here. Now we're just sketching the curve, so the y values are not going to be exact, nor am I looking for the exact y values. They should be close, but they won't be perfect. On this set of axes, I'm going to plot all three of these, because I know that we're crossing the x-axis at the zeros. So at negative 4, we have a 0. At negative 2, we have a 0. And at 2, we have a 0. So we cross the x-axis at these 3 points. I think we know that we have a 0. We might not cross the x-axis, but we definitely have a 0 at those points. So on our number line, we have at negative 4, our function is 0. We have at negative 2, our function is 0. And at 2, our function is 0. Now here, this interval is going to be that x is less than negative 4. We have x is between negative 4 and negative 2. And x is between negative 2 and 2. And x is greater than 2. So we're going to split up our number line into these 4 intervals. We have x plus 4, x plus 2, x minus 2, and then p of x, which is a product of all 3 of these values. Now what I'm doing here is I want to know where this function is positive and where this function is negative. So remember that if p of x is the same thing as y. So if p of x is positive, then our y is positive, which means we're above the x-axis. So I want to know where my function is above the x-axis and where my function is below the x-axis. So we're going to check each of these intervals. If x is left of negative 4, then we see that x plus 4 will be negative. We can use a test point. Let's use negative 1,000. Negative 1,000 plus 4 is negative. Negative 1,000 plus 2 is negative. Negative 1,000 minus 2 is negative. So a negative times a negative is negative. This means that p of x will be negative to the left of negative 4, because it's the product of 3 negatives. If x is between negative 4 and negative 2, so we can use the test point negative 3, because it's between negative 4 and negative 2, Negative 3 plus 4 is positive. Negative 3 plus 2 is negative. And negative 3 minus 2 is negative. So we have a positive times a negative for our p of x, and that gives us a positive. So that we know that p of x is going to be above the x-axis on the interval negative 4 to negative 2. Then we check between negative 2 and 2. We can check 0. It's the easiest point. 0 plus 4 is positive, 0 plus 2 is positive, and 0 minus 2 is negative. Positive times a negative is negative, so p of x is below the x-axis on this interval. And then we test to the right of 2, so we can pick 1,000. 1,000 plus 4 is positive, 1,000 plus 2 is positive, and 1,000 minus 2 is positive. So we have a positive times a positive gives us a positive. So on the interval where x is greater than 2, we know that p of x is positive. We show you here. I'm breaking up this interval. These red lines are not a part of the graph. I just want to show you sort of what we know. We know that p of x is negative. So p of x is down here below the x-axis. On the interval from negative 4 to negative 2, p of x is positive. So p of x will be up here above the x-axis. Between negative 2 and 2, p of x is negative. So on this entire interval, p of x is less than 0, so it's below the x-axis. And then when x is bigger than 2, p of x is positive. So we'll be up here on this interval. So we know it's going to go something like this. But what do we know about the end behavior? We already talked about end behavior earlier. What do we know about it here? Well, we have an odd degree for our p of x, n is 3, and we have a positive leading coefficient. So n is equal to 3, and a sub n is positive. It's greater than 0. It's equal to 1. So we know that our end behavior should be down over here and up over here. Does that make sense with what we have seen so far in the graph, where p of x is negative, positive, negative, positive? Yeah, it makes sense. Going down on the left side, when we have p of x being less than 0, should make sense. So let's go ahead and graph this now. We should get something that looks like this. So we are negative here. We go up to, we become positive between negative 4 and negative 2. We're negative between negative 2 and positive 2. So we come back down. And then we're positive after 2. So our graph will look something like this. All right, I want you to try one now. Factor p of x, find the end behavior, and sketch the graph. If p of x is equal to negative x cubed plus 9x. The next topic I want to talk about is the shape of the graph near 0. Definition: the multiplicity of a 0, c, in p of x is the number of times x minus c appears in the factorization of p of x. What I really want to talk about here is the shape of the graph for different multiplicities of roots. Shape of the graph near zeros of multiplicity m. If c is a 0 of p with multiplicity m, then the shape of the graph of p near c is as follows. Multiplicity of c, if m is odd and m is greater than 1, then we'll see this type of graph. We'll either have it going from bottom to top, we might be going from top to bottom. This might remind you of something, and it should. It should remind you of these graphs up here, way back at the beginning of the lecture, where if we have an even, then you touch the x-axis and you bounce back. If you have an odd, where we had a higher than 1 odd degree, then you have this little squiggle that goes through the x-axis. Well, that's the same idea here. When the multiplicity of c is odd, then we have this little squiggle that goes through the root c. Now, depending on what the graph looks like and where the other roots are, we could be going bottom to top and squiggling through, or top to bottom and squiggling through. We'll see an example in a second, but let me finish this part here. If we have that m is even at c, we might come down. We'll touch the x-axis, and we'll go back up. Or we'll come up, touch the x-axis, and go back down, like this. So these are the different types of multiplicity. These are the different types of intersections of roots C with different multiplicities. Now let's do an example just to try to cement this a little bit. Sketch the graph P of x. P of x is equal to x minus 2 times x plus 1 squared times x plus 4 cubed. There's a few things I need to note so that we can figure out the end behavior. First, what's the degree of this polynomial? Well, the degree would be the highest degree after we've multiplied it all out. If we multiply this one out, the highest degree will be 3. If we multiply this one out, the highest degree will be 2. So when we multiply everything together, we would have an x cubed times an x squared times an x to the first power. So we just need to add up all of the degrees. X to the first, x squared, and x cubed. So we would actually have degree 6. Our leading coefficient, a sub n, is going to be positive. So we can say that we are going to either, since we have an even degree, our end behavior will be up, up. So as x goes to infinity, y is going to go to infinity as well. As x goes to negative infinity, y goes to infinity. So let me go ahead and draw this out a bit. So at x equals 2, we have a 0. At x equals negative 1, we have a 0. And x equals negative 4, we have a 0. So these are all of our zeros. We know this because these are the roots that appear in the factorization of p. How many times do each root appear? Well, x minus 2 appears once, x plus 1 appears twice, and x plus 4 appears 3 times. So we go back to here, and we look at their multiplicity. The multiplicity of x minus 2 is 1, so it does not squiggle as we go through. M is odd, but m is not greater than 1. It goes straight through. So we're either at 2, we're either going to go straight through like this, or straight through like this. At x equals negative 4, we're going to squiggle through. We're either going to go like this through, or we're going to come down and squiggle through like this. It's one or the other. And then at x equals negative 1, we're either going to come down and bounce back up, or we're going to come up and bounce back down. One or the other. How do we figure out which way we go through each 0? Well, we know that our end behavior as x goes to infinity is going to be up, up. So we're starting at our least 0, the most negative 0, which is going to be x plus 4. So we know we come down. We're coming down. And we squiggle through because we have a multiplicity of 3. And then we come to x equals negative 1. And we're going to come down, touch the x-axis, and we're going to come back up. And then x equals 2, because the multiplicity is only 1, we get this. So this is what our graph is going to look like. Something like this. We come down, we squiggle through x plus 4 because we have multiplicity 3. We touch and return at x equals -1 because we have multiplicity 2. And then we go straight through x equals 2 because it has multiplicity 1. Right? I want you to try to do the opposite. Use the graph to find the function. Use the graph to find the function with the lowest degree possible. Right? So what I mean by that is we could, if we saw this on a graph and we didn't know what the polynomial was, we could guess that this was a multiplicity 3, could be a multiplicity 5, or a multiplicity 7. It depends on how flat it is. Because it's hard to draw these as flat as they need to be, we can assume that this is multiplicity 3 when we're looking for the lowest degreed polynomial that has this type of graph. That's what I mean by the lowest degree. So here's the graph. And this is a squiggle through 0. So keep that in mind. Right, the last topic I want to talk about is local max and mins of polynomials. Definition. The point a f of a is a local maximum if f of a is greater than f of x for every x in an open interval containing a. The point b f of b is a local minimum if f of b is less than f of x for every x in an open interval containing b. Now we've already discussed what these are, local max and mins, at least what they look like on graphs. So if you have a function that looks like this, we would have a local maximum here and a local minimum here. The y value of this point is lower than any y value corresponding to x values surrounding this point. And the y value of this point is higher than any y value corresponding to x values around this point. So what we're saying here is that we have a local min here and a local max here. Local extrema of polynomials. If p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down to a sub 1x plus a sub 0 is a polynomial of degree n, then the graph of p has at most n minus 1 extreme values. Now, extreme values are just local maxes and mins. What this is saying is that we have at most n minus 1, the degree of the polynomial, minus 1 extreme values. There's no more than that. Is it possible to have fewer than n minus 1? Absolutely. But we cannot have more than n minus 1. Try one. What is the maximum number of extreme values for the function f of x equals x to the 4th minus 3x cubed plus 4x squared minus 12x plus 28? I'm just asking for the maximum number of extreme values. You don't need to tell me how many there actually are. All right, that's going to be it for today. I will see you all in the next lecture.